Actually, what I want to talk about is coming next to Thomas. What he's talking about is levels. What is the levels of certain products? But before I do that, I actually want to show some design, because sometimes we forget that if we don't have what we are doing and all these things we're doing, if we don't make real changes to the geometry, it doesn't have any meaning. We need to sometimes also have the components in mind when we're doing all these analysis stuff. Because what we are dealing with here is not trying to talk about analyzing, trying to solve, no, we want to change the design, because if there's no changes, what are we doing? So I want to start with actually going very deep into one single interface. This is just very shortly the company that I'm from. Valcon Design is a member of the Valcon Consulting Group. We are 300 people, and we have three divisions. We have management consulting. This is why we are talking so much about trying to measure how good design is, because that actually makes it some kind of controllable. Then we can manage it, then we can scale it, we can train people. And then we have the design departments where I'm the head of. And OMT, that's another story. They are making ships. I'll not talk about that right now. Just one little teaser here. Maybe everybody has seen it, but each time I see it, new things are coming up. Because this little example here, one aspect of robust design that I have found is extremely important, I'll not say it's everything, but it's close to, is over-constraints. When we have over-constraints in a design, suddenly we have this situation. Let's assume we had 0 production tolerances. Then we could assume then we have no problems. No, we don't, because what Thomas is talking about, load deformation, thermal variation, all this stuff will actually try to make this different. And then we have this situation. And we all know it. And each summer we need to put some new in. They're changing all the time. From a perspective of robust design, this is a non-robust design solution. It's born like that. No analyze, no simulation, nothing can remove it. It can improve it, but it cannot remove it. And there's a huge difference there. So what I'm talking about now is really digging into the over-constraint part. For one, it's simple. You don't need to calculate anything. It's so simple. But it has such a big advantage. So I want to look for one example of how is the over-constraints and how is that looking. If we have a guy here, if we look into such a product in low volume, I would expect that we have a 100,000 leg table. This is what we're talking about. There are so many over-constraints in such a product. My argument is not that we can remove all of them, but I would assume that we can remove around 90 to 95% of these over-constraints. Let's dig down to one single interface between 2 components of the weight of approximately 5 grams. It's in an automotive company. They're producing 5,000 interfaces like that a year. And I would say it's 1 out of 1 million or even more companies. And this is how their design is looking today. I have the 2 components here. I have painted all the surfaces green. These are the surfaces that we need to have control of more than 500 of a millimeters to actually have a good product here. Let's look into their drawings. These guys are amazing to be able to produce. They are stretching, injecting molding to a level that I have never seen before. They are able of producing 0.025 millimeters on 10 millimeters in the injection molding. Steady production. What they achieve by doing that is a varying scrap rate in average of 5%. That is not a good situation to be in. Let's look into how could this look by a design perspective. Let's not do any simulation. Let's not do any calculation. No, let's change the way the design is looking, because that is what's needed here. No simulation can change these two parts because they are simply wrong. So they have not deserved any analysis, they have not deserved any simulation, they need to be changed. And this is what we do before we start simulating. So let's set up a specification, because we know what we want to end in. We know what the specification of an injection molding, we know how that is looking, we know what is easy to produce. So why start designing before we actually know what the result should be? Because we know that up front. We need that all surfaces which doesn't touch each other, all the non-green surfaces, should actually be to IT15, because that means that we have no quality control on this. There should be no functional surface between tooling halves. Tooling halves in such an injection bowl, they actually have clearance, meaning that we will have clay inside. So that is not a situation. We know that from the beginning. This is no geometrical demands beside length. We all know these GPS measurement where you have the roundness, the planarness. It's beautiful signs. They're very complicated. Let's have designs where we don't need any of these. Each time I see a design, each time I see such a thing, I'm glad I can read it. Flatness, this one, there's a lot of these signs. Let's just get rid of them. Let's use them where we want, but let's make design where all these are non-needed. So this is the goal for the design. Let's look how this looks. This is how it's looking. So this is a compliant solution, and back to your KPI, this is actually a solution which will score very, very high. It will be insensitive to temperature, it will be insensitive to load deformation, it will have a totally another story of tolerances. But I will come back to that. This is the part we had on the left side, which was demanding all these tolerances. This is the part on the right side. Now look how small surfaces, if you look into a Lego block, they are there. I would claim that everybody thinks that Lego is the best in the world due to their production. I would claim it's due to this. I'm not sure they can produce the tolerance I just showed you in this automotive company. I'm not sure about that. I'm actually sure that they don't need to do it because they have such a beautiful little dot in their Lego block. It's a beauty. Can't help them. They're just damn good at it. This is the next one. On the left side, we have the original. On the right side, we have the other one. Let's look at the drawings now. This is how it's looking. We haven't made any simulations. And we have now a situation with the scrap rate below 0.00, and we have tripled the tolerances. This is live. And when we then start looking at how is the component out there, how is the component in general in the industry, because this is just one example. In this company, this is average, how the components are looking. We have looked into, this is just another example, an old example, I've made them myself, but this is an old example, how components are looking when we design it this way. If we look into the companies and say, we can have huge results of implementing Six Sigma where we really bring down the variance, we can have that. Huge results. And it's very effective, and we should do it. Personally, I don't like the discussion if it's this or the other, because it's both. But you could imagine that, back to this one, it's a little complex to actually do that. It needs some kind, well, there are some measurements to control here. So what happens if we don't have the right design is that cost is going up. Cost of inspection, and I'll actually also claim innovation is going down. And the reason for that is that if you get the experience that each time you do something new, things go wrong, you'll be in a position where the best is not to do anything new. I can understand that, because the guy who made this solution I showed, he has worked with that solution for 1.5 years with no progress. Ask him to do a change. He said, no. Now it works. I don't know why. I will not change anything. So this is actually hitting our innovations. So what we are saying is, and back to the scale, what we are saying is, let's work out here. Let's put some metrics on what is good design, 6 data compliant design, which I just showed you some example of. How's that looking? And then let's go into this and secure that we have a very robust. We call it Design for Six Sigma. There's a lot of good works on this. I'll claim that on the basis, I'll come back to that, of 20,000 interfaces beside the industry, this is a blind spot. It's not out there. We can talk about processes. We can talk about we're doing it all right, but when we are going out there and measuring how is the result, it is not there. Sorry to say, it's not out there. So we have analyzed 20,000 interfaces in medical, automotive, aerospace, energy, defense, and customer industry, and some others. And we have made a scale. It's a very easy one, because what we do is we say, here is an example, we have 2 components. It's for a hearing aid. These 2 components should just be fixed together. That means that we have in mechanical language, and that is mechanical language, we have 6 degrees of freedom, 3 translation, 3 rotation. It's nothing more. There's just a lot of them. So this is where the complex comes in. In this situation, we need 6 constraints to lock this. 29 is used. So we have 23 legs on the table here, too many. Looking a little further, the total number of this is 101. It's not that much. Actually, it's above average in the industry. And the index that we made, which is very simple, you just take this number and divide it by the number of interfaces. You have now an index of 14. Let's come back to that. Looking at our customers and how they are seeing the situation, we have defined this ranking scale. So let's start down here. Below average, above 20. We have very large issue-driven effort on constant new and changing problems. I will say that a lot of engineering is in that situation. Then we have very large effort on manning and changing issues, large effort on several but repetitive. Now we come some control. But we still use a lot of effort. And of course, the no surprises, maybe that is a little too populistic, but at least as the goal, we should be there. When we look at the cost saving, this is average, what we see, because when we suddenly jump up, we can really lower the cost, because the inspection and all that demand is really, it's going away. That was it. And I'll just say, have a nice day. Any questions? Come back. Yeah.
I noticed your green contact surfaces.
Yeah.
They are large, where there's over-constraint. They are very small in your ideal solution.
Yeah.
But could that not be a problem with deformations
yes.
and local overload,
yes.
which can give cracks, in, for example, in plastic parts?
Yes, it could.
So there are issues which are beyond your index.
No, but I'll come back to that. That can be an issue. This is the surfaces you need with the forces for this one. Okay? So this is calculated. So the area of the minimal surfaces is exactly what you are claiming there, is the demand for strength. So what I'm saying here is that this was the situation of the surfaces we needed. So what I'm saying is that in 99%, when we see components like that, we like to believe that it's because it's really well thought. I'm sorry to say, it's not. This is surfaces which is made not by purpose, but they're just there. So it's not well thought. This is a solution where it's well thought with respect. So in the index, you're not allowed to do surfaces smaller than exactly what you're saying there.
But if you have the large surface, you don't need to think about local load.
Oh, but you need to think about a lot. Because in reality,
You move the problems to another area.
no, because in reality, large surfaces doesn't exist. Because you will never have two parallel surfaces. That means in reality, the non-parallelity of the surfaces bring you in an uncontrollable situation with small surfaces. So the situation you are describing is just, sorry to say, it's wishful thinking, because it doesn't exist in the real world. It's the same when we suddenly say, a lot of production people would like to say, me as a trader, I wanted to be able to orient the different ways. And I say, no, you don't want that. Because no parts are symmetrical. So why do I need, I just take your cup of coffee, why do I need, when I have a system like that, why do I need it to be oriented and making a jeopardized roulette inside with this variation? No, I don't need that. It will be totally fixed in the same position in all 6 degrees of freedom, every time. Yeah. Other questions?
I'll weigh in with one then. Along the same lines of thinking, how is it affected by the some deformations of flexible parts? Are we a bit more okay with having multiple contact surfaces when we have flexible parts?
Yeah. What we're doing is we're working with 3 levels of robustness, our methods. The first level is where we work with everything as if it was totally rigid elements. This is to find what I call the logic in the mechanical. It's to find the kinematics, it's to find how the forces are going. This is level 1. Coming back, let's assume that I should do, I've done a scanner like that, 1.5 meter scanner, with small bars tracking the paper. Having 2 bearings like that, and then a demand of deflection of 200 of a millimeter, maybe that will demand an axis like that. I don't like that. But nevertheless, in level 1, I will say that I need these 2 bearings. But then I know, I need the 3rd one, because else it's wobbling. This is level 2. So now I suddenly go from, is it rigid or not? And then I find the over constraint. And in these over constraints, we apply what we call a stiffness matrix. We multiply a stiffness matrix with a movement matrix. When you do that, you get a reaction matrix. And then we calculate on the reaction matrix, finding out, are now the parts breaking, or do we have some other problems? And then we start doing solutions on level 2. If we can't get that to fix, we go to level 3. In level 3, we go to the situation where we talk about that test, simulation, and geometry should fit. And then we are finished, and then we have a verified design. So this is the, how can I say, the process behind. Yeah.
Yes,
Yeah.
I totally agree with you. I've been working with these type of things for many years, a lot in the automotive industry, and I've seen that in the automotive industry they use locating schemes. They know where to put the contact because that's where you distribute variation. But if you go outside the automotive industry, it's totally unknown. They don't know about 6 degrees of freedom, and this is 6 degrees of freedom. And this is nothing that you can discuss. It's not a social problem.
No, it's not. It's non-discussable.
It's not a social problem. So, but when you analyze all these interfaces with all these companies, do you see similar that in some type of business, some type of industry, they understand these things, and in some it's totally new?
Yes.
I feel personally that it's 20 years difference between some of the companies.
I see exactly the same. And to be honest, I also see another thing. I think we were better in the old days.
Yeah. When we had real engineers.
Sorry. I have analyzed the clock for the 40s. And the writing machines, they are damn good in designing. Unfortunately, they didn't have that good production system. But maybe that was where they were that good. Because when you don't have a production, have you seen what production can do? They can do a press fit of a gear wheel with 1,000th of a millimeter in difference. It's amazing what these guys can do. But why should we use it? I don't think we should use it. But back to your question. When we look in the automotive industry, this is where we have seen levels up here. Not in general, but we see it. But it's like, okay, there it is. And there it is. We haven't seen, most of it is above average, and very seldom there's one or the other. Because what we see is that even in automotive, it's not really controlled by top management. So it's more like built in the organization, and it's a culture, and it's so some of the young guys suddenly forget it a little bit. So we see the automotive up here. I would say the best score we have ever seen is a pump of 2 for automotive, a water pump for a car in automotive. Then we see most industry down here, and when we go to, sorry if there's any, but when we go to machine builders and these things, they are down here. Molding tools, something like that. It's really, they are very low on this. So we see it, and we can track it. Yeah.
Are there any final questions? In that case, let's thank you very much.